Applications of physics are literally everywhere, but probably the most ubiquitous topic, the one that has the most applicability to everyday life, is circuits. We're constantly surrounded by circuits, by electronics. From mobile phones and computers to light fixtures and refrigerators, they really are everywhere. Electronics can get pretty complicated, but they're all based on some very simple concepts: voltage, current, and resistance. Welcome to Flip Physics. Today I'm going to talk about circuits. A circuit is a general term for something that moves in a circle, or a loop. In the case of electricity, it's electrons that are doing the circulating. The circulation in your body is about the flow of blood. And in fact, anything where liquids are flowing provides a very good analogy for the way circuits work. There are three things that we like to measure when we're dealing with circuits. Three things that are super useful to us. One of them, resistance, we'll get to later. The other two are voltage, otherwise known as electric potential difference, and current. Voltage is the energy transferred per coulomb of charge. A taller water slide will mean that more energy is transferred per kilogram that goes down the slide. And in exactly the same way, a higher voltage battery means that each coulomb of charge will transfer more energy as it moves around the circuit. So voltage is energy transferred per unit charge, work divided by charge. And therefore 1 joule per coulomb is the same as 1 volt. Voltage on its own isn't that powerful and also isn't that dangerous. The Van de Graaff generator that you can use to make your hair stand on end can have as much as tens of thousands of volts running across it. But to be electrocuted, you need that charge to flow. You need some current. Current is the flow of charge measured in amps. It's defined as charge Q divided by time t. 1 amp means you're transferring 1 coulomb of charge per second. Or in other words, 1 coulomb of charge is moving around the circuit each second. So this is kind of like the water flow. You might have 1 kilogram of water flow down the slide each second. Current is a measure of the rate at which something flows. In the case of circuits, this thing is charge. And if too much charge flows through the human body, it hurts. Be careful out there, kids. Since physicists sometimes lack artistic skills, we can make simple diagrams of circuits using these symbols. So this circuit, for example, has 3 resistors and a battery. The long line in the battery symbol represents the positive side of the battery, and the shorter line represents the negative side of the battery. So, a circuit is a continuous flow of charge. That charge, those electrons, come from a battery. But we didn't always know that it was electrons that moved around a circuit. We used to think it was positive charges that moved. Because of that, when we say current, what we actually mean is conventional current. Conventional current is the flow of positive charges around a circuit. Positive charges will be repelled from the positive end of the battery and attracted to the negative end of the battery. This, of course, is absolute tosh. Positive charges don't move around the circuit at all. It's negative charges, electrons, that do the moving. The electrons move the opposite way. But for old time's sake, for historical reasons, we pretend that it's positive charges moving around the circuit. I guess people are just too lazy to change it. Or too uncoordinated. Probably both. So far we've talked about voltage and current. The third new term is called resistance. Resistance is how much a component, whether a bulb, resistor, or something else, how much a component in an electrical circuit resists the flow of current, resists the flow of electricity. A strong resistor won't let charges flow around the circuit hardly at all, and a weak resistor will let them flow nice and smoothly. I guess going back to our water slide analogy, this will be kind of like putting obstacles on the water slide for the water to go around, or making the water slide rougher, adding more friction. Resistance is measured in ohms with this symbol, and for most resistors we can calculate it using this equation, where R is the resistance of the component measured in ohms, V is the voltage across the component measured in volts, and I is the current flowing through the component measured in amps. This equation works whenever a resistor is said to be ohmic, which most resistors are. It's a pretty easy equation when you have a nice simple circuit like this. The A in this diagram represents an ammeter, a device that measures the current flowing through it. The V represents a voltmeter, which is currently set up to measure the voltage or potential difference across the bulb. The difference in potential on each side of the bulb. The voltage the bulb is receiving. Let's say the voltmeter currently reads 9 volts because this circuit has a 9 volt battery. And let's say the current flowing through the ammeter is 4.5 amps. Then the resistance of this component, the resistance of this bulb, must be 9 divided by 4.5, which is 2 ohms. Pretty straightforward. We could also use this simple circuit to figure out how much power it's using. If we remember from previous videos, power is the energy used per second, work divided by time. And you might also remember that it's measured in watts, or joules per second if you prefer. But in circuits, there's another way of calculating it. Power is voltage multiplied by current. So this could be the total power of the circuit, or it could be the power used by an individual component, like the bulb. In this really simple circuit, that number is exactly the same either way. To figure out how much power this circuit is using, we'd take the 9 volts and multiply it by the 4.5 amps. And that would give us 40.5 watts of power. In this case, that's the power used by the circuit, but it's also the power used by that bulb, because the bulb is the only thing in the circuit. But what happens with more complex circuits, circuits with more than one component, like these? For those, we need to know what happens to voltage and current in different parts of the circuit. We need to talk about parallel and series circuits. But before we move on to those more complex circuits, now would be a good time to pause, review, and make sure you understand the basic concepts of voltage, current, resistance, and power. Once you're ready, you can click here to continue. Thanks for watching Flip Physics. If you like this video, you can press the like button. You can also subscribe or go to the flipphysics.net website. But most of all, don't forget to leave a comment below with your questions, thoughts, and suggestions. Until next time, keep questioning. Maybe Serenity should actually be the name of my all-teacher summer band. Titles like No More Grading, and Chairs Have 4 Legs, and Party After 9.